I'm John Hartwig. Ken Mitchell and I are excited to share with you the following slides on AMD Ryzen processors which power today's game consoles and PCs. Let's begin. Today's agenda includes an abstract and speaker biographies, products, data flow, microarchitecture, best practices, and optimizations. First, the abstract. Join AMD for an introduction to the Ryzen family of processors. Learn about Ryzen products, dive into instruction sets, cache hierarchies, resource sharing, and simultaneous multi-threading. Discover profiling tools and techniques, and gain insight into code optimization opportunities and lessons learned with examples including C++, assembly, and hardware performance monitoring counters. Some introductions to start. I'm John Hartwig. I'm a senior member of the technical staff and CPU team lead in the AMD Game Engineering organization. My day job is to help game developers like you optimize for AMD processors. This means analyzing game code and providing tips on things like memory use and engine threading. Today I'll be your guide through best practices and optimizations learned through that analysis. But first, I've invited Ken Mitchell to cover products, data flow, and microarchitecture.
Thanks, John. Hello, my name is Ken Mitchell. I'm a principal member of technical staff and technical lead in the AMD Software Performance Engineering team, where I collaborate with Microsoft Windows and AMD engineers to optimize AMD processors for better performance per watt. But frankly, I'm more about performance. My previous roles included optimizing PC games for AMD processors, analyzing PC applications, and developing system benchmarks. Here we go. Products. AMD Ryzen 7000 series mobile processors. The AMD Ryzen 7045 series, formerly codenamed Dragon Range, is for extreme gamers and content creators who want many powerful Zen 4 cores with discrete graphics. The AMD Ryzen 7040 series, formerly codenamed Phoenix, is for elite ultra-thin laptops. These processors are built on the cutting-edge 4nm process node to deliver the best performance battery life you can get in an ultra-thin laptop. They also include powerful Zen 4 cores, fast RDNA 3 integrated graphics, and the new Ryzen AI engine. The AMD Ryzen 7035 series, formerly codenamed Rembrandt, offers astonishing battery life for premium thin and light laptops thanks to its Zen 3 cores and RDNA 2 integrated graphics. The AMD Ryzen 7030 series, formerly codenamed Barcelo, delivers serious hardware for mainstream thin and light price points. Its Zen 3 cores and integrated Vega Radeon graphics support entry-level esports gaming at 720p. Finally, the AMD Ryzen 7020 series, formerly codenamed Mendocino, leverages Zen 2 core architecture and RDNA 2 graphics for everyday computing. AMD is committed to years of future support for the new Socket AM5 platform packed with state-of-the-art technologies such as high-speed DDR5 memory, PCIe Gen 5 support, AMD Expo one-touch memory overclocking, and AMD Ryzen 7000 series desktop processor support. These desktop processors, formerly codenamed Raphael, are powered by the Zen 4 core microarchitecture. 3 new processors with AMD 3D V-Cache technology offer a massive gaming performance boost thanks to larger L3 cache. Eco Mode and 65-watt low power models have leadership efficiency. Formerly codenamed Chagall Pro, AMD Ryzen Threadripper Pro 5000WX series Zen 3 processors deliver an unmatched CPU core density for professional workloads, tear through complex rendering and visual effects projects while increasing creative iterations, reduce compile times, and get more done in less time. Data flow. First, this slide shows an abstract diagram of a Zen 4-based AMD Ryzen 9 7940HS mobile processor, formerly known as codenamed Phoenix. Imagine data moving from DRAM on the far right through the data fabric, caches, and cores on the left. Each unified memory controller manages 32 bits of DRAM. DDR5 5600 and LPDDR5 7500 are supported. In this monolithic die SoC design, the orange-colored Core Complex L3 cache connects to the blue-colored data fabric at 32 bytes per cycle read and 32 bytes per cycle write. RDNA 3-based integrated graphics, a multimedia hub, and an inference processing unit are present in this mobile processor. Some ultra-thin gaming product configurations may feature up to 9 teraflops of single precision integrated graphics performance at 120 gigabytes per second memory bandwidth. Next, we have an abstract diagram of a Zen 4-based AMD Ryzen 9 7950X desktop processor, formerly known as codename Raphael. Each core complex die in this chiplet design has a unified 8-core cluster with a massive 32MB L3 cache. Each unified memory controller manages two 32 bits of DRAM. A DIMM is composed of two 32-bit subchannels. DDR5 5200 JEDEC is supported. Faster memory speeds are possible using AMD Expo technology. Some product configurations may feature up to 1 teraflop of single precision integrated graphics performance at 83 gigabytes per second memory bandwidth. Thus, the included RDNA 2-based integrated graphics are for basic desktop and office use. We recommend a discrete graphics card for gaming. Next, we have an abstract diagram of a Zen 4. Finally, this slide shows an abstract diagram of a Zen 3-based AMD Ryzen Threadripper Pro 5995WX 64-core 128 logical processor, formerly codenamed Chagall Pro. This product has 8 channels of DDR4 memory and 128 PCIe lanes. You can add many GPUs and NVMe drives to this beast. This topology with up to 8 CCDs is so large that I've shown it in quadrants for simplicity. This product requires a discrete GPU. Microarchitecture. Advances in Zen 4 microarchitecture include a 13% IPC improvement using typical desktop applications, a larger op cache to deliver more ops per cycle, a larger L2 cache, an improved load store unit with a larger load queue, branch prediction improvements with larger branch target buffers, and AVX 512 instruction support using a 256-bit data path. To improve instruction throughput, the processor implements simultaneous multithreading, SMT. Single-threaded applications do not always occupy all resources of the processor at all times. The processor can take advantage of the unused resources to execute a second thread concurrently. Although each thread has a program counter and architectural register set, core resources may be shared while operating in two-threaded mode. The core is in two-threaded mode while its two logical processors execute program threads. If either of the core's logical processors execute the operating system's idle thread, it may return to single-threaded mode. Disabling SMT and system BIOS menu options will reduce the number of logical processors in the system and limit cores to operate in single-thread mode. Resources such as queue entries, caches, pipelines, and execution units can be competitively shared, watermarked, or statically partitioned in two-threaded mode. These categories are defined as competitively shared. Resource entries are assigned on demand. A thread may use all resource entries. Watermarked. Resource entries are assigned on demand. When in two-threaded mode, a thread may not use more resource entries than are specified by a watermark threshold. Statically partitioned. Resource entries are partitioned when entering two-threaded mode. A thread may not use more resource entries than are available in its partition. Resource entries are unpartitioned when exiting two-threaded mode. Caches and TLBs are competitively shared for Zen 2, Zen 3, and Zen 4. For Zen 3, the integer scheduler, integer register file, and load queue have changed from competitively shared to watermarked. For Zen 4, the floating point physical register has changed from competitively shared to watermarked. These changes improved SMT fairness. Consider profiling both recommended spec and min-spec CPUs, which may have different SMT fairness. Zen 4 added GFNI and AVX 512 support. More details are on the next slide. Please note, AMX instructions are not supported. Zen 4 AVX 512 support includes many ISA extensions which may benefit workloads such as light baking, texture compression, and neural networks. AVX 512 FP16 is not supported. AVX VNNI using VEX rather than EVEX encoding is not supported. Use software prefetch instructions on linked data structures experiencing cache misses. Use NTA on use-once data. While in two-threaded mode, beware too many software prefetches may evict the working set of the other thread from their shared L1 data and L2 caches. Prefetch T0 and NTA fill into the L1 data cache. Prefetch T1 and T2 fill into the L2 cache, a new feature for Zen 4. For previous generations of Zen processors, prefetch T1 and T2 filled into the L1 data cache. Cache details, including ways, associativity, inclusion policy, and write policy, are described in AMD software optimization guides. Designing data structures that match hardware prefetcher access patterns may improve performance. The L1 data cache, stream, and stride prefetchers are my favorites. Stream prefetchers may fetch additional sequential lines in ascending or descending order. Stride prefetchers may fetch additional lines when each access is a constant distance from the previous. The L2 cache also has an L2 stream prefetcher. Additionally, the up-down prefetcher may fetch the next or previous line. This simple example may trigger a streaming hardware prefetcher as it iterates the contiguous array. Similarly, iterating standard vector may also trigger this prefetcher. Two strides are detected in the code samples shown. Again, iterating standard vector may also trigger this prefetcher. However, the stream and stride code snippets may not trigger a hardware prefetcher if they iterated instead using a linked data structure with nodes scattered randomly across memory addresses. Zen 2 increased the L3 cache size and micro-op cache size. Zen 3 further increased the L3 cache size. Zen 4 further increased the micro-op and L2 cache sizes. Some Zen 3 and Zen 4 products feature X3D technology for larger L3 caches, which are great for gaming. For example, the Ryzen 7 7800 X3D 8-core processor has a single 96 megabyte L3 cache. The AMD Cache Coherency Protocol is MoESI, Modified, Owned, Exclusive, Shared, and Valid. Instruction execution, speculative execution, prefetching, and external bus transactions may change the cache's MoESI state. Read hits do not cause a MoESI state change. Write hits generally cause a MoESI state change into the modified state. If the cache line is already in the modified state, a write hit does not change its state. The AMD Zen 4 microarchitecture implements a large L3 cache shared by up to 8 cores inside each CPU complex. The L3 cache maintains L2 cache shadow tags for each L2 inside the complex. The shadow tags determine if a cache-to-cache transfer between cores is possible inside the CCX, which is fast. Cache coherency probe latency responses may be slower from cores in another CCX. Minimize ping-ponging modified cache lines between cores, especially in another CCX. Here are a few tips. 1. Minimize using read-modify-write instructions. Use a single atomic add with a local sum rather than many atomic increment operations. 2. Improve lock efficiency. Test and set in user spin locks, or replace user spin locks entirely with a modern sync API. And 3. Use a memory allocator optimized for multi-threading. The memory manager is a big repeat offender for contention of locking primitives. Try memalloc or jmalloc. Some AMD products may have cores that are faster than other cores. AMD calls this feature preferred core. The system BIOS may describe the ACPI CPPC highest performance ranking for each logical processor. These values are the basis for the get system CPU set information scheduling class values in Windows 10 and later for some AMD products. Windows may use scheduling class during thread scheduling. Scheduling class values may change during runtime. For some AMD products, the fastest logical processor number may be different on another serial number part for the same OPN, such as AMD Ryzen 9 7950X3D. Logical processor 0 may not be the fastest core. CCD 0 may not contain the fastest core. Thread affinity masks may interfere with thread scheduling and power management optimizations on Windows PCs. I typically recommend not setting process affinity or thread affinity masks in PC applications. Back to you, John.
Thanks, Ken. Now that you know what the hardware looks like, let's figure out how to make the best use of it. Prefer shipping, or at least test build configurations, over development or debug builds for CPU profiling. Development builds can greatly decrease performance and cause you to spend your debug time on false alarms. Stats collection may cause cache pollution, causing you to look for cache problems in the wrong places. Logging can create serialization points, and many debug builds may disable multi-threading optimizations. Sometimes, while investigating open issues, developers may submit change requests which enable debug features on test and shipping configurations. Be sure to disable debug features before you ship. While we're editing the build settings, it's a good idea to take the time to disable anti-tamper while CPU profiling. For CPU performance profiling, you should build a binary similar to shipping configuration, but without anti-tamper or anti-cheat, which may prevent CPU profiling tools from properly loading symbols. It's important to test the cold shader cache for the first-time user experience. Be sure to clear the application shader cache if it has one. The end user will often not be running the same scene back to back the way we as developers do when debugging. The example shown clears the Microsoft, AMD, and NVIDIA shader caches. Reboot after running this script to clear any shaders still in system memory. Applications and games may vary configurations of shader caches on disk, yielding different results. Results may also vary based on GPU vendor and driver version used. Use the latest compiler in Windows SDK. This ensures you get the latest build and link time improvements. Rebuilding Unreal Engine 4.27.2 is much faster on Visual Studio 2022 and 2019 compared to 2017. Some developers have experienced larger benefits than those shown. Also ensure you're using the latest C runtime optimizations, especially for memcopy and memset. Recent Visual Studio 2022 updates improved indexing performance and vectorization. Windows Defender scans can greatly slow down some workflows. Windows 11 enabled the Windows Defender Sandbox feature by default, which greatly improved security, but also increased file copy and file compress times. Add project folders to virus and threat protection settings exclusions for faster build times. This system showed a 20% reduction in build time by adding folder exclusions. That said, warning, this recommendation is for personal development systems and not for continuous integration and continuous deployment systems. Putting this all together, using the latest compiler and SDK, with virus and threat exclusions properly set up on your local build folder, can make a huge impact in the real time you spend each day waiting on builds. A binary may have better code generation using AVX or later ISA by using the Microsoft Visual C compiler option ARC AVX, AVX2, or AVX 512. The minimum hardware requirements for Windows 10 include SSE2. For Windows 11, it is only SSE 4.1. The Windows 10 supported processor list includes AMD products which support AVX, but not AVX2. The Windows 10 supported processor list may include products from other CPU vendors which do not support AVX. Enable AVX 512 in development tools such as light baking, texture compression, and mesh to sign distance fields. We observed a 17% performance increase thanks to AVX 512 while using the Intel Embry path tracer with ISPC. Audit content. Ask artists to recommend scenes of interest for profiling. For example, an indoor dungeon with heavy occlusion, an outdoor city, an outdoor forest with alpha transparency. large crowds, or a specific time of day. Unreal Engine developers may find some performance issues simply by running map check, especially for issues related to actor shadows. Unity developers may enforce minimum standards using the asset postprocessor. Check your stats before CPU profiling. If the scene far exceeds its draw budget or has many duplicate objects, especially duplicate physics objects, consider reporting the issue to its artists and profile a different scene. Otherwise, you may risk profiling hotspots which may not be hot after the art issues are resolved and the scene is completed. Additional considerations may be necessary to ensure the expected GPU is utilized in hybrid graphics platforms. The Windows 10 Spring 2018 update added enum adapter by GPU preference. Use DXGI GPU preference high performance for game applications. The user may change preferences per application in Windows graphics settings. Prefer H.265 video and ACC audio codecs as recommended by the Unreal Engine Electric plugin. Hardware accelerated video codecs may increase hours of battery life and reduce CPU work. Please note, the WMV3 codec is not hardware accelerated in recent products, such as Radeon RX 6500 XT, Radeon RX 6400, and AMD Ryzen 6000 series mobile processors. If you are using WMV3 content, please replace it with H.264 content, which may provide a better user experience. Optimizations. Some modern sync APIs, such as the standard mutex, may leverage AMD's mwaitx instruction to efficiently wait on an address or timeout. Legacy sync APIs, such as wait for single object, may have additional syscall overhead. This microbenchmark shows significant performance improvement by using the standard mutex rather than wait for single object. Core isolation memory integrity, otherwise known as virtualization-based security hypervisor protected code integrity, may have a significant performance impact. Windows 11 ships with this feature enabled by default to provide stronger protections against malware. The wait for single object function checks the current state of the specified object. If the object state is non-signaled, the calling thread enters the wait state until the object is signaled, or the timeout interval elapses. Thus, wait for single object may not suffer from OS thread scheduling and core resource sharing issues caused by some bad user spin locks. This is because user spin locks may consume OS thread scheduling resources unnecessarily, since the OS scheduler may be unable to determine if it should yield to another program thread or continue to spin. As a result, user spin locks may starve other ready threads doing payload work. Functions like standard mutex are faster than wait for single object. Many of the modern sync APIs can live in the user mode, avoiding costly syscall instructions, and even better, most can compile into fast instructions like mwaitx on Ryzen CPUs. Many of the classic functions are designed to call into more costly syscall instructions. Some of these have been around a long time and may have legacy compatibility reasons why they cannot be optimized as well as the more modern ones. Here's the source code for the main function using the exclusive lock microbenchmark we'll reuse in the next few slides. Basically, it times how long it took all threads to execute the callback function. User spin locks may consume OS thread scheduling resources unnecessarily, since the OS scheduler may be unable to determine if it should yield to another program thread rather than spin. One of the most obvious trademarks of a bad spin lock is a while loop that does not include a pause instruction. They consume core resources in an overly aggressive manner, doing non-payload work that starves other ready threads. They can also consume a lot of power. For notebook users, This can translate into real hours of battery life during gameplay and a reduction in the power budget that your game may need on the GPU. If you have to live with a spin lock, there's a few ways you can improve them. Test, then test and set, add pause instructions, and align the lock variable. This is the most basic example, but in order to fully optimize your spin locks, you may want to go a step further. It can often be beneficial to align your pause count to the latency of a pause instruction on your target hardware. For Zen 2 architectures, an optimal place to start might have been somewhere in the range of 140 cycles. Try running a number of spin pause cycles on your loop. If you still don't have your resource, and you're still waiting, then this might not be the quick, low overhead lock you thought it was. So put the thread to sleep and have it signal wait. You did your best. Low overhead work had a chance to return quickly, and it didn't. It's now best to yield this core until the resources are available. A good way to achieve this behavior, without committing to a fixed number, is to implement it through an exponential backoff. Wait for single object with create mutex are shown in this example. These two APIs have been around for a very long time. The wait for single object function checks the current state of the specified object. If the object state is non-signaled, the calling thread enters the wait state until the object is signaled, or the timeout interval elapses. Thus, wait for single object may not suffer from OS thread scheduling and core resource sharing issues caused by some bad user spin locks. Note, this example requires some initialization in main. Better yet, standard mutex is even faster than wait for single object. This modern sync API is based on a slim reader-writer lock in Microsoft's implementation, which can be verified using the Windows Performance Analyzer. In my testing, standard shared mutex and enter critical section also outperformed wait for single object. Update your compiler for the latest memcopy, memset, and other C runtime optimizations. Memcopy behavior is undefined if the destination and source overlap. However, the compiler may generate repmove string instructions which have defined overlapping behavior. Alinus 64 may allow for faster repmove string microcode. Alinus 4K may reduce store-to-load conflicts. The processor uses linear address bits 0 through 11 to determine store-to-load forward eligibility. STLI Other in Microprof counts store-to-load conflicts where a load was unable to complete due to a non-forwardable conflict with an older store. Additionally, Alinus 4K may benefit probe filtering on AMD Threadripper and EPYC processors. Finally, aligning to the bit floor, clamped between 4 bytes and 4K bytes, may provide a good balance of cache hits and alignment. Threading. Simply put, write code that scales to the cores your user has in their PC. Underthreading is bad. Unlike consoles, PCs don't have one single config, so avoid hard-coding thread pool sizes on PC. While we're at it, overthreading is also bad. Creating too many threads can cause thread migration and lock contention. In a perfect world, we can scale all the game systems to the logical processor count. PSO compilation, in fact, often can be scaled that wide quite nicely. However, games are not the stupidly parallel workloads that synthetic benchmarks are. They're a complex series of interconnected systems. Games often suffer from SMT and cache contention on the main or render threads during gameplay. As a result, it can often be beneficial to tune some of the game systems to scale to the physical core count to reduce this contention. Note, this advice is specific to AMD processors and is not general guidance for all processor vendors. On Ryzen, the AMD core count sample at GPUopen.com is a great place to start. There's no hard and fast rule, and every game is different, so profile your game to determine the ideal thread count. Game initialization, including decompressing assets and compiling and warming shaders, may benefit from logical processors using SMT dual thread mode. However, gameplay may prefer physical core count using only SMT single thread mode on systems with at least 8 Ryzen CPU cores. This is based on our own experience with the most recent games of the past couple years and is subject to change. We've seen some games improve frame rates by 5 to 10% thanks to this optimization, but actual results may vary. Be careful with affinity masks. These generally interfere with OS scheduling and power management. If you lock a single high priority thread to a core and the thread stalls, then the core stalls. Idle cores mean lost cycles. It's often better to let the OS float low priority work across cores, filling idle blocks as they come. This also still allows for critical threads to preempt as needed. We often prefer priority over affinity masks whenever possible. As an added benefit, the user may experience more hours of battery life when gaming without affinity masks. This makes this guidance extra meaningful when tuning not just for frame rate, but also for hours of gaming while on battery. Priority is the order in which threads are scheduled. It's often much better as it allows work to float across cores. There are still things to look out for though. 1. Be careful not to starve the OS. Know the priority levels your target operating system uses for critical functionality and avoid them. Generally, game systems aren't important enough to starve core system functionality. Watch out for priority boosts, which can sometimes be called when waiting on critical sections. A boost will temporarily increase a thread priority range by 1. Staggering your priority ranges by 2 can help control this behavior. A small range, for example mapping low to 1, medium to 2, and high to 3, would mean that a boosted 1 could effectively become a 2. If it frequently waits, it may become a semi-permanent medium priority game task. This is likely not the intended behavior here. We usually want a boosted low priority task to jump to the front of the low priority line, but we don't want it to cut in front of other medium priority tasks, or worse, for a medium priority task to cut in front of our highest priority things. As a tip, if you suspect you have an issue here, try simply disabling the set thread priority boost on all of your threads. If perf goes up, you may have an improper range or some inappropriate boosts. Data access. False sharing is the usage pattern that occurs when 2 cores update data within the same cache line. Unlike true sharing, such as shared pointers and globals, where the author of the code is explicitly sharing something between cores, false sharing can occur without a function author realizing it. The classic example is when 2 locks share the same cache line. This is very common in tightly packed arrays. If you suspect false sharing on a variable or lock, try aligning it to the size of a cache line, which is currently 64 bytes. This micro-benchmark showed its execution time reduced by 90% after optimization. For this example, each thread accesses a single thread data element within an array. Before the optimization, the array was compact, but unfortunately, different threads frequently modified the same cache line while using their thread data in the callback function. Simply padding each thread data using a line as of the native cache line size resolved this issue. Use software prefetch instructions for linked data experiencing cache misses. In this example, performance improved by over 60% using software prefetch optimizations. Results may vary significantly for systems with different cache sizes or different memory latency. The NVIDIA PhysX Kappa demo iterates a standard vector of pointers. Consequently, the stream and stride hardware prefetchers are of little help due to the pointer chase. Before the optimization, many of the data accesses in the innermost loop missed the 4 MB last level cache of the AMD Ryzen 7 4700G. Since the convex class member data is not public, offset of keywords cannot be used, and thus literal offsets are shown. Although not illustrated in this example, additional performance may be possible by reordering the hot member data to occupy only one cache line rather than 4. There's a significant penalty for mixing SSE and AVX instructions when the upper 128 bits of the YMM registers contain non-zero data. Transitioning in either direction will cause a microfault to spill or fill the upper 128 bits of all 16 YMM registers. There will be an approximately 100 cycle penalty to signal and handle this fault. To avoid this penalty, a V0 upper or V0 all instruction should be used to clear the upper 128 bits of all YMM registers when transitioning from AVX code to SSE or unknown code. In this example, benchmark execution time was reduced by 60% after a V0 upper optimization. Use the floating point dispatch faults PMC event to find code which may be missing V0 upper or V0 all instructions during AVX to SSE and SSE to AVX transitions. Here are 3 simple optimizations which may mitigate this performance issue. First, use the architecture AVX instruction flag. AVX is supported by 95% of users according to the December 2022 Steam Hardware and Software Survey. However, this may not be a viable option for software with very old SSE2 minimum hardware requirements. Second, return an M256 value using pass-by reference in the function parameter list rather than the function return type. And third, use force inline on the function definition. Any of these changes may allow compiler optimizations to reduce floating point dispatch faults. Here's an excellent example of the floating point dispatch faults issue encountered in the mesh to SDF benchmark. Both the before and after optimization examples are compiled using the default architecture SSE2 flag. Before the optimization, the function return type is an M256 value. After the optimization, the M256 value is returned using pass-by reference in the function parameter list. Using AMD Microprof, we can quickly find the hot line of source code and its assembly code. In this example, the rightmost column is the floating point dispatch faults per 1,000 cycles, which is greater than 0. Looking at the assembly code, we can see there's a variable blend packed single precision AVX instruction, which is soon followed by a move align packed single precision SSE instruction, where the upper 128 bits have not been cleared by a V0 upper or V0 all instruction. This needs optimization. After the optimization, the M256 value is returned using pass-by reference in the function parameter list. Using AMD Microprof again, we can find the same line of source code and its assembly code. We can quickly observe floating point dispatch faults per 1,000 cycles is 0. Awesome. The compiler has inserted a V0 upper instruction between the variable blend pack single precision AVX instruction and the move align pack single precision SSE instruction. The performance issue is resolved. Do you want to know more? Discover your best graphics performance by using our open source effects, SDKs, tools, and tutorials at gpuopen.com. Software optimization guides for Zen 2, Zen 3, and Zen 4 are available at developer.amd.com. Got questions? Email us We'd love to hear from you. Design faster, render faster, iterate faster. We can't wait to see what you create.